All right, guys, it's Day Daddy here, and just want to start as always by saying thank you guys for taking interest in my channel. I really hope the content provided is useful for you. If it is, I'd really appreciate it. Hit that like and subscribe button so I can continue to grow and provide more quality content. Now we got that out of the way, let's hop into today's topic. Today we will be talking about Bluetooth security. Specifically, we'll be talking about a particular paper I've read recently. It is called Bluetooth with Low Energy Comes Low Security. So without further ado, let's hop in. So the claim in the paper is that Bluetooth low energy or Bluetooth smart encryption can be rendered useless. And you may be thinking, well, is that really possible? And as it turns out, yes, it is. So we're going to start with a brief introduction to BLE to get some fundamental principles that will help in understanding the rest of this talk, the rest of the paper, and really just Bluetooth BLE security in general. So what is BLE? BLE is a short-range communication protocol that's used in over 9 billion devices and counting. It's Bluetooth Low Energy, or BLE, or Bluetooth Smart. Those are all synonymous. And that's really talking about Bluetooth version 4.0 and above. And the distinction here is it's Bluetooth 4.0, or the release of Bluetooth 4.0, really is kind of the splitting of, or parting of ways. So there's Bluetooth Classic, which is 3.0 and below, which is kind of its own protocol. And then with Bluetooth 4.0, there was a new, almost sub-protocol release called BLE, or Bluetooth Smart, which is designed to work with low-energy devices. It's a reduced protocol and has some pretty serious security issues because it's reduced and it's really designed to work on those low-energy devices. Just as a note, BLE is not the only protocol, or Bluetooth Smart is not the only protocol going forward. Bluetooth Classic, the more robust protocol, is still maintained and still has version releases and version updates, but this marks the split where there's two different almost distinct protocols. Okay, so now I got that out of the way. Oh, and by the way, before I forget, I do have another video that outlines the Bluetooth protocol in a lot more depth, and I will leave the link in the description for this video if you're interested. But anyway, so BLE and Bluetooth Classic both operate on the unlicensed ISM 2.4 gigahertz band. And the Bluetooth Classic has 79 channels. Bluetooth Smart, or BLE, has 40 channels spaced 2 megahertz apart, and we can kind of see that here in this nice image in the bottom right-hand corner. So 37 of those channels are data channels, and then 3 of those are advertising channels. And one thing to note here is the spacing of the advertising channels. And on the next slide will kind of make more sense, but basically, since we're operating on an unlicensed band, a lot of other protocols are also operating on this band. So Wi-Fi, Zigbee, other protocols you've probably heard of as well, are all operating on the same band because it's unlicensed and doesn't cost money. So as you can imagine, the interference on this channel, on this band, could be quite high. So various protocols have different ways of minimizing that interference, and with BLE and Bluetooth in general, one of the ways they do that is they try to at least space the advertising channels in such a way that they kind of miss the major Wi-Fi channels. So that's kind of why you notice that this is on the edge of this Wi-Fi channel here, and this is kind of in between, and there's one here on the extreme end, so that the spacing itself lends itself to minimizing the interference. Okay, so that kind of leads us into this idea of frequency hopping. So another interference minimization technique that Bluetooth employs is this idea of frequency hopping. So basically, every second, a master and a slave, or 2 connected Bluetooth devices, will change channels 1,600 times in random order, which is designed to, like I said, minimize interference and also make the channel more robust. So you may be thinking, okay, well, if they're changing channels 1,600 times, how are they staying on the same channel so they can communicate with each other? Well, Before a connection is established, a master and a slave, or two Bluetooth connected devices, will kind of agree on a particular sequence that they're going to carry on with going forward. As we can see here, they may start on channel 9, and they'll hop to channel 21, and they'll hop to channel 35, but both devices are hopping in the same order at the same time, staying on the same channel. And this allows for further reduction in interference with other protocols that are on the same band, and also with other Bluetooth devices or other Bluetooth connections that may be happening in and around. So I think that's a nice illustration for that. That's the basic idea of frequency hopping. Okay, so now that we've discussed that, let's talk a little bit about the Bluetooth packet structure. So for the general Bluetooth packet, we have a preamble, which is basically an 8-bit 1 byte series of zeros and ones that are alternating 1 0 1 0 1 0 1 0, or the opposite. This is just kind of a more or less a spacer. I read somewhere that this actually can indicate whether the packet is an advertising packet or a data packet, but I don't really trust the source, so take that with a grain of salt. The access address is this address here for advertising packets. It's always the same, and then for packets, the data channel packets that are sent after connection, it is some unique value that is established upon connection, and that'll become more important later as we talk about the security implications that go along with that. Okay, and then finally, the same thing that you're going to see in all the packets is a CRC, which is a cyclic redundancy check, which is used for error detection and error correction, and that'll come into play later as well. And then we have in the middle here, we have this PDU, or protocol data unit, which carries the user data. And then for advertising channels, there's a 2-byte header, and then a particular payload, a smaller payload, and then with PDUs for data channels, there's another 2-bit header with a larger payload, which includes an MIC. So BLE does have encryption, and its encryption is normally used, and this MIC's message integrity check is used for encryption and security on the BLE protocol. Okay, so now we understand the basics, let's talk a little bit about eavesdropping. So that's going to be a big concept going forward, in a way that we can basically listen to and get BLE packets, decrypt them, and generally crack the key exchange process. So let's talk about sniffing. So how can we follow the BLE connections as they hop across the channels? Well, and also how can we what parts do we actually need in order to sniff these packets and follow these packets across the length, or across the entirety of a connection? Well, we need the hop interval, which is referred to also as dwell time. And that hop interval is basically how long two connected devices are on a particular channel. There's something called the hop increment, which is basically when you switch, so when they finally move from one channel to the next, how many channels do they move? So they go from 1 to 7, or 1 to 5, or 1 to 3. What is that interval? There is the access address, which we already kind of talked about. And then this CRCInit value, which is the initial CRC value that is used, and we'll discuss that a little bit more later. That'll make more sense. But we need those 4 values so that we can actually make these. Even if we sniff the packets, we can actually use them. And normally, this would require us to witness the initiation of a connection. And since at least the advertising packets and the connection initiation are in plain text, those values as long as we can see the connection, we can retrieve those values. However, in this paper, one of the interesting things is they have developed a novel procedure, basically, to retrieve this information even when you can't see or you haven't, you have no record of the connection initiation. So, and we'll go through that as well. Okay, so how do they actually perform it? What is the physical hardware that we need to actually perform this sniffing? And then the device they use in the paper is called Ubertooth, and it's a cheap open source network sniffer. It's basically comprised of a USB dongle, an RF front end, which is basically the antenna, a CC2400 radio chip, and a small LPC microcontroller, all built into the device. So the highlights here is that this is a low-cost hardware. A lot of other Bluetooth sniffing hardware cost thousands, if not tens of thousands of dollars, or at least they did at the time of writing this paper. And I mean, actually, I checked, and that's kind of still the same case today. But basically, this was a low-cost option. It's not as robust as some of the others, but it's low cost. It does require tighter timing requirements because we can only listen to one channel at a time with this sniffer. Okay, so now we have the hardware. We have kind of an idea of what we're trying to do. So how do we actually make sense of these bytes? We've got the hardware to get the signals. Well, now we need to modulate or demodulate the signals and turn that back into bytes and then and bits. So the CC2400 radio chip demodulates the signals collected by the antenna or the RF front end, and basically demodulates that with GFSK, Gaussian frequency Gaussian frequency shift keying, with a frequency offset of about 250 kilohertz and a rate of 1 megabits per second. And from my understanding, these are just values that you can key into the Ubertooth, and it will just demodulate all those for you, and it will spit out packets, basically, that you can further analyze. So the way that they did this, the way that they started, is they tried to identify the start of a transmission, or the start of the bytes of interest. And remember, we talked about the advertising packets all have the same access address of 0x8e89 bed 6. So that's the same for every advertising packet all the time. So it's very easy to key in on, and very easy to look for. So the start of the transmission is identified by one of these addresses, and then also, we can verify the end by looking for a second one of these addresses, or one of these series of bytes. And you may be thinking, well, Spencer, what about that first preamble bit? Well, yeah, that's in there, and that's actually one of the things they cited in the work that they could have maybe improved on, but really it's not important because we know that it's there, and as long as we know what the series is, we can subtract that number of bytes out and gather all of the important data that's in between. So not really a huge issue there. Okay, so how do we follow these connections? That's what I talked about earlier. And in order to follow the connections, we have to hop the channels or the sniffer has to hop the channels in the same order as the master and the slave, or whatever two devices that are connected. So to do this, we need to know the hop interval, and we need to know the hop increment, and basically to get to the next channel we need to go to, we need to take the current channel, add the hop increment, and then mod that by 37. There's only 37 possible channels, and that will take us to the next channel. As you can see here, we have the master and slave going between different channels, and this is how we're getting to the next channel. And so in this way, we are kind of following using this formula here. Okay, so the previous defined step, or the things that we just went over, are kind of the easy way, when we have been able to see the connection and we have access to that data. So we've been able to get all 4 of those points that were necessary to decrypt the packets, basically. But what if we don't? So in this case, in promiscuous mode, as they coined it in the paper, this is when we don't have access to that information. We have to find it retroactively. So let's go through that process. So the first step is determining our access address. So we're going to monitor an arbitrary data channel, and we're going to look for some empty data packets. And we're looking for these because they're predictable and they're transmitted frequently. You may think that, so basically as you are transmitting these packets, most of them are going to be empty packets because the data transmission is fairly sparse. So these empty packets have a very predictable signature, a very predictable byte structure. So basically, we have that 16-bit header we talked about earlier, and we have the 24-bit CRC. If the payload is empty, except for that header, basically, and the only variance is there's 2 bits in the header, 2 flags that are SSN and NESN. And those are the only 2 bits of variability really that we have. So we're kind of keying in on 14 bits of this 16-bit header. So that's what we're trying to key in on here, and we're looking at that in the byte stream that's coming in. And basically, once we've found that, we'll treat the prior 32 bits, so the prior 32 bits to that 14-bit match that we have, and that we will treat as the candidate access address. Now, since we're only keying in on 14 bits, there's a high false positive rate. So what they did in the paper to combat that is, rather than just taking the first access address that they found, that first 32 bits, they basically stored all of the different candidate access addresses that they sniffed. And then after observing a particular one 5 times, which was an arbitrary value they chose, they kind of selected that as the target candidate access address that they were going to use going forward, and they were going to filter for. Okay. So similarly, we need to find a way to recover this CRCInit value that I talked about earlier. So we're going to do something similar in this case. We're going to recover the hop increment and hop interval, the hop increment and hop interval are sensitive to timing and ineffective in the presence of false positives. So that's why we need this value. So we want this to verify basically that the packets we're looking at are the correct packets, because these CRC values are going to be unique. And so filtering by the CRC can help us with that. But to do that, we need to make sure we have the right CRC values that are associated with the particular connection stream. So the CRC is calculated using what's called linear feedback shift, or a linear feedback shift register, LFSR, which is preceded with the CRCInit value. So basically, like whenever the connection is established, the CRCInit value is generated, and then the packets are kind of pushed through this this LFSR, and then output is a new CRC value. So imagine we have the new, we've sniffed the CRC value, or the new CRC value that was generated. So we can actually reverse this process, reverse this LFSR process to get back to the CRCInit value. And that's, it's a little bit more complicated than that, but essentially all that you're doing is you have initial value, you're shoving bits through, and you're offsetting them by 1 every time. And then whenever you shove everything through, you're left with a new CRC value. So all you have to do is shift the bits the opposite way to get back to the init value. And they do this a number of times, and once they observe the same one 5 times, they say, okay, this is the CRC value that we want, or CRCInit value we want, and they're going to treat that as true. So kind of a similar process to what we did with the access address from before. Okay, so now we need to figure out how to get the hop interval. That's the third value of interest. So a hop sequence, or one time all the way through the 37 channels, which is called a full cycle, completes a full cycle every 37 times 1.2 milliseconds times the hop interval. This is all in milliseconds. So basically, the idea is we're going to stay on a particular channel, and we're going to measure the time between packets, and we're going to use this formula to back calculate the hop interval. So it's pretty simple. You're on a particular channel, you measure the time that you observe a packet, you wait some time, and then you observe a packet with the same access address. Okay, well whatever that delta t was, you stick it here, and then divide it by 37 times 1.25, and then you get a hop interval. All right. Now let's talk about the hop increment. And this is a little bit complicated. I'll do my best to explain it. But basically, so we're going to start on data channel 0, or a particular data channel. I think this is actually arbitrary, but they specified 0 in the paper. I don't know that it really matters what channel that you actually start on. But the idea is you're going to start on data channel 1. And then once a packet arrives, you're going to jump to another data channel. Call it data channel 1. Sorry, I think I misspoke. So you're going to start on channel 0. Once a packet arrives, you're going to hop to a different channel, channel 1. And then the hop interval in time is known. So we already know that. So we can basically back calculate how many channels were hopped between 0 and 1 using this formula. So we know the delta t, we know this constant here, and we know the hop interval from the previous slide. And now we can basically back calculate the number of channels that are hopped. Okay, so now here's where things get a little bit more complicated. So now we need to find the hop increment, which is different than the channels hopped. This is the actual, the physical number of channels that are incremented from the original channel. So basically, it's going to be channel 0 plus the hop increment times the number of channels hopped equals, or I guess exactly equal to 1. Then we're going to rearrange, and we can find that, okay, the hop increment is actually exactly equal to the inverse of the channels hopped mod 37. Okay, so the hopping sequence is isomorphic, so multiplicative inverse of channels hopped is well defined. And we can use Fermat's little theorem to yield the following closed form, which is channels hopped inverse 1 is exactly equal to channels hopped 37 minus 2 mod 37. And basically, all of this math, I mean, you don't really have to follow all of this, but the takeaway here is the fact that there is a mathematically a certain way, or a mathematically defined way, where we can find the hop increment. Okay, and then that hop increment is stored in a lookup table, because this outputs 36 possible values, and then we're going to put that in a lookup table to prevent all of this mathematical computation every single time. And all we're going to do is, based on the channels hopped, we're going to look up whatever one of the 36 outputs are, and then we're going to map that back to a hop increment. Okay, so now that we know the two ways in which we can calculate, or we can get the necessary values. One is by observing the initial connection. One is by passively gathering data and then kind of reverse engineering. How do we actually bypass the encryption? Because this is the important part. Because once the connection is made, everything is all of the packets are encrypted. So how do we get around that? Okay. So session encryption is actually AES CCM, which is virtually impossible to crack. So the session itself is very safe. The weakness, however, is in the actual key exchange protocol. So Bluetooth Special Interest Group, or SIG, or the organization that actually came up with Bluetooth and standardized it, decided that they would invent their own key exchange. So it's a 3-stage process, and the pairing method depends on the first stage. So there is a just works method of pairing, there is a 6-digit PIN which is used in pairing, and then there's an OOB method. So it actually says in the documentation, and you can go and look this up, it says that none of these methods protect against against passive eavesdroppers, which I thought was really interesting, that they would publish this in documentation and move forward with this key exchange, even though they know that this is a possibility. So I thought that was pretty interesting. But basically, in the first two cases, so the just works and the 6-digit PIN, the just works, the temporary key used when they're initiating a connection is always 0. So that takes absolutely no time at all. There's no mystery in that whatsoever. So that's just known. The temporary key is an integer value between 0 and 999,999. So not really a lot of keys there either. So basically the way that they did it in the paper is no matter which, like if it was this just works that was chosen, well, that's a dead giveaway. They already have the temporary key, so that's trivial. And then slightly less trivial, but still not a very hard problem, is when they actually use the PIN, which is 0 or some value between these two numbers, and that's an easy brute force problem. So they would brute force that, and then once they found the temporary key, well, now they have the temporary key, and all this other information is already known. These are just other variables that are passed in this AES encryption algorithm. So the rest is kind of history. It's a really simple problem as long as these are the two most common pairing methods used, and you've just basically reduced both of them to something trivial. So anyway, very easy to get. In fact, as a fun exercise, you can guess how long it actually takes to crack this particular PIN one, and surprise, surprise, it's less than 1 second in the absolute worst case. So, and they ran these the brute force algorithm on an Intel i7 CPU. So not even a supercomputer, just some normal computer you would probably have laying around your house. You can crack this in less than 1 second. So I mean that's more or less. There's a little bit more nitty gritty, but that's really the long and short of it. Is once you have this temporary key, you can find the short-term key. Once you have the short-term key, you can find the long-term key, and once you have the long-term key, you can find the session keys. And all this is done 100% passively. So again, the temporary key is kind of the key to finding out everything else, and then decrypting the whole schema falls apart when you get this temporary key. So there were a few caveats listed. This technique is ineffective against a well-chosen OOB key, and that's actually done. This key is transmitted off-band. So they didn't go into detail about what this technique actually is, but apparently it's beyond the scope of this paper. But apparently it's not very commonly used, so take that for what you will. Second, if a master and slave establish an LTK or a long-term key, they don't really need to reestablish one, and they can continue using the key exchange protocol. So what that means is if they've already gotten to the step where they have a long-term key and you don't already have it, well, there's not going to be a chance for you to go back and get that. Similarly, there is a session-specific nonce that's exchanged at the beginning. So even if you have the LTK, or even you have the long-term key, then you may not be able to, or you actually won't be able to decrypt the session once it's started. So both of these are problems that they encountered. However, they theorized that this can be overcome by basically forcing some sort of connection reestablishment. So in one instance, like for the first case, you can inject an LL reject IND packet, or basically a reject packet, reject the connection, and then that will trigger the connection to be reestablished, and then you can either sniff the connection establishment and get those 4 values, or you can passively do it if you for some reason miss those packets again. So basically, it's like getting another try at being able to get the temporary key and then work your way up to the long-term key. And then finally, if they're already in the session, then you can just jam the signal. Apparently, they were using some sort of signal jammer, and it was very effective. They would jam the signal, and then connection would be reestablished, and they were able to actually break that new encryption that was started with the new connection. So, couple caveats. A lot of this was theoretical. I'm not 100% sure if they actually were able to physically test that. That wasn't clear in the paper. But either way, just food for thought that this is not a 100% perfect technique that works all the time. And then just some of my general comments. This paper was written in 2013, and it's been quite a while since then. And we're actually in Bluetooth version 5.3. So my question was, are there any security improvements between I think 4.1 or 4.2 is when this was released, and now. And I looked through the documentation in Bluetooth 5.3, and which came out in 2021, by the way. And there wasn't a whole lot of new security features or improvements that I could see. There was one new option to increase the pin size or the key length size. There was a couple other small security advances, but nothing that seemed to say that the weakness in the key exchange was fixed, which is even more alarming because now the Bluetooth transfer rates are over 50 megabits per second, and the range is over 700 feet. So that's like 2 football fields or more that they can now be sniffing your packets and taking advantage of this security vulnerability. So I thought that was very interesting that it's been so long and nothing seems really to have been done. And then finally, just as a critique for the paper, as I kind of mentioned earlier, there was a lot of theoretical musings about things that could be done or might be possible, especially with respect to the mitigation and counter mitigation techniques. They also discussed briefly packet injection, which they used as kind of a counter mitigation strategy, and they didn't appear to have actually tested that either. They just said that it was possible, and it was difficult. So I wish they would have expounded a little bit more and maybe done some testing. And one other just musing as well, it would have been nice to know how effective or how often they were actually able to successfully decrypt the packets. Like, what was the success rate on average? That would have been a nice thing to know, but that was not anywhere in the paper. So finally, I just want to give credit where credit is due. The link to the paper, if you're interested, is this link. I'll pause just for a moment so you can take a picture or type it in your URL or whatever. I'm also going to link it in the description if you'd rather go that route. And then finally, I had a bunch of other sources I used, some other papers I referenced, and then just some general web articles and blogs that I thought were very helpful. So I'll pause again just for a second and let you guys take a look. I'll link those in the description as well. All right, guys, thank you for watching. Again, if you are interested in more about the Bluetooth protocol, I have another video. It should be linked in the description if you're interested about the protocol in general, its history, how the versions have changed over the years. Might be helpful. If you didn't understand some of this, it might answer some of the questions that weren't answered here. Anyway, thanks again, guys. I really appreciate it. If you enjoyed the content, please consider giving me a like or subscribe so I can continue to grow and produce better content. And also, please don't be shy. Give me some feedback in the comments. Let me know what you like, what you don't like, if something's unclear, if there's anything I can improve upon. But again, thanks, guys. Have a great rest of your day, and I'll see you next time.